Hey guys, BuildZoid here, and today we're going to be taking a look at the GTX 1080 Ti Strix from ASUS. Before we get into this, I just want to say I want it. I really, really want this. And we'll get into the reason why right now, actually, because I've decided we're not going to do the usual scribbling all over all the unimportant stuff and then looking at the actually cool things. We're going to skip straight to the reason why I like this card so very much. This right here is the V-Core VRM for this card. Yeah, and I mean, it's not the most incredible V-Core VRM ever put on a GPU, but it is already very, very nice. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 phases achieved through a doubling scheme, obviously, as you can't actually make a 10-phase VRM using a, well, one of those, which is a UP9511P, but really, just 9511 is what you'll, like, that's what it, like, there's an extra letter on the actual IC, but that letter is not part, like, the data sheet doesn't care about the extra letter at the end. So it's the 9511, and that is a 8-phase voltage controller with 600 kilohertz switching frequency. So it's actually a relatively, it's a pretty slow voltage controller. Some of the really high-end stuff goes up to like 2 megahertz. So 600 kilohertz is not incredible, but this is the voltage controller pretty much required by NVIDIA. There's a few others that can be used, but NVIDIA, basically the UP9511 is used on the Founders Edition cards, and it is pretty much required by NVIDIA. So it's not surprising to see it here, and it is a bit sad that it only does 600 kilohertz, which actually for this card means that after the, like, you basically, because we're not doing 8 phases, we're doing 5 times 2, that means you're actually, the maximum switching frequency that the phases actually end up with is going from 600 kilohertz to 300 kilohertz, which means that in terms of power quality, theoretically, a 6-phase running 600 kilohertz switching frequency would be cleaner. Same goes for a 7-phase and a 8-phase, assuming that they still have the same power throughput capabilities and are using MOSFETs of similar quality level, because obviously if you use cheaper MOSFETs at higher switching frequency, you won't necessarily achieve the same level of voltage regulation, just because the MOSFETs impact how much power you lose, and so, yeah, and how basically it impacts the ripple characteristics of that phase. So yeah, if they're still using the same kind of MOSFET quality, then the 6-phase at 600 kilohertz should beat this right here, but it won't beat it for power throughput. And these chips right here should be very recognizable to anybody who's been following the PCB breakdowns for a while. These are none other than the International Rectifier IR3555. ASUS really likes to use these, which is a great thing, because these are 60 amp power stages, and that 60 amp rating is available at 125 degrees centigrade. So yes, your VRM can run very, very hot, and at 300 kilohertz switching frequency, which pretty much means you're guaranteed that 60 amp current continuous. That's continuous. These can peak in the 90 amp range, but so you have 60 amps continuous at 125 degrees, 300 kilohertz, which basically means this VRM right here is capable of doing 600 amps for the V-Core, which is ridiculous overkill for a 1080 Ti, because if you've seen any of the reviews, then you'd know that the 1080 Ti runs on about 200 to 270 watts under load, depending on, you know, what exactly you're running on it. 270 would be like the hardest part of Firestrike or Furmark, or, you know, whereas 200 would be like average gaming load, sort of 200 to 230 would be like average gaming load. And of course, some of that power has to go to all of these, all of the GDDR5X memory chips, so that means the GPU core is only really pulling around the 200 amp range, which means that you have a V-Core VRM that is 3 times more powerful than necessary, which translates into the fact that there is literally no way you're overloading that VRM. Like, no way, no chance. Good luck. I really wish you good luck with that. Even on LN2, a 1080 Ti will not pull anywhere close to 600 amps. You might be able to get the current draw to double. Well, actually, you might be able to get it within 100 amps of that, but like you're not gonna actually hit 600 amps continuous. And then, of course, it, you know, if by some miracle you got that high power draw, that's the continuous rating. So you can actually spike significantly above that for short periods of time, ranging around, I think it was 10 milliseconds at 90 amps per phase. So you can really, like, you can push these cards a lot. Way more than NVIDIA allows you to, because of course they are completely locked down as far as software voltage control goes, but we will be talking about some of the other reasons why I like this PCB so much, and we'll go into the details on that. So yes, the V-Core VRM is amazing and incredible, and I really, really like it. So now let's move on to the other, much more boring stuff. Right under the V-Core VRM, we have the PLL, and this is a necessary voltage for the GPU core to function. It doesn't actually do anything for overclocking. It's not worth, you know, really worrying about. Down here, this is probably the 5-volt VRM. Now, this exists because that runs on 5 volts. These run on 5 volts. I'm pretty sure this runs on 5 volts. And there's just a whole bunch of circuitry on the card that runs on 5 volts. And unfortunately, all of your power, all of your GPU power is put through this little connector here. And that only provides 12 volts and 3.3 volts. Which means if you actually want to do any, like if you want to run any of the other 5-volt devices on this GPU, you need a whole extra VRM just to power them, which is what this right here is. So again, not really worth worrying about. It doesn't do anything for overclocking. It's just necessary for the card to function. And next to that, we have what I suspect to be the 1.8 volt rail. So these might be swapped around. And the 1.8 volt rail is required for some of the internal PLLs of NVIDIA GPUs, as well as the BIOS chips actually run on 1.8 volts. And I wonder if ASUS isn't using this 1.8 volt VRM to also supply the... There's an extra voltage that is required by GDDR5X to function. I suspect this VRM might be providing that too, based on the fact that I can't find the, like, usually there'd be a VRM sort of in this area of the card which provides the other 1.8 volts for the GDDR5X, but I can't find that, and it's certainly not up here, as that's a filter. That's not a power choke. That, like, you can tell because there's a 16 volt cap in front of it, so basically have power, 12 volt power going through that, which then goes to this VRM right here, which is the GDDR5X VRM. So that's a 2-phase. And that is using FD, so these guys are FDPC. Oh, yeah, they are PC. So FDPC 5018SGs. And these are dual NFAT, dual NFATs. That's really the best way to say it. So basically, one of these ICs contains 2 N-channel MOSFETs, and one MOSFET acts as the high side, one acts as the low side, and they're integrated. So that's sort of the idea behind that. Now, these right here, theoretically, the VRM would be able to deliver a maximum of 88 watts, but that would be with 8 watts heat output on each of the, like, on the FATs. So might have a hard time actually keeping that at, oops. That was supposed to be 88 amps at 125 degrees centigrade, of course, and assuming 300 kilohertz switching frequency. And so the thing about that 88 amp figure is you might actually end up not being able to cool them. But at lower current throughputs, these will basically, like, not put out any heat at all. And I actually think my heat calculation breaks down because it forgets, like, driver switching losses and stuff like that for these because it works out to 1 watt if I stuff in 30 amps. So I'm going to look into that, but yeah, very, very efficient. And that's also the reason why you don't see any, like, there's not a whole lot of real heat sinking anywhere on this card, mostly because this is really efficient. GDDR5X memory chips are really, really efficient. That's one of the reasons why they were made. This VRM is not even providing, like, it has to provide barely 30%, like, roughly 30% of its total current capacity. So this thing runs, like, this is going to run really, really cold as well. As this is going to be, like, it's technically slightly below its peak efficiency curve, because peak efficiency is always achieved around, like, just the way the parts are designed, they're designed to hit peak efficiency at around 50% load, maybe a little later. So, yeah, this is going to run ice cold as well. So, yeah, you know, very, very nice PCB from ASUS. Extremely overkill. But that's not the only reason why I like this card, because there are cards out there that do more overkill. Currently, actually, for the 1080 Ti, I haven't seen any that are more overkill than this, but that's mostly because I haven't seen any of the other custom cards, and I am certain that once EVGA puts out the classified, that's going to have the usual EVGA 14-phase classified VRM, so that'll obviously be a contender for most powerful VRM on a 1080 Ti. There's almost certainly going to be a 1080 Ti Kingpin, 1080 Ti Hall of Fame. Gigabyte tends to go kind of insane on their phase count, so I wouldn't be surprised if we see something crazy from them as well. MSI is sort of taking it pretty, like, they're not putting out bad stuff, they're just putting out reasonable stuff. Like, this is ridiculous overkill. MSI would go for like 400 amps on an 8-phase design or something instead of 10. So, yeah, but that's, you know, so basically the VRMs are not the only reason why I really like this card. The other reasons are, there's a BIOS switch up here. Admittedly, it's missing, but it's there, which means, theoretically, you should be able to put that, like, solder your own BIOS switch on, and depending on how that's wired, you might be able to put an extra, you then have to get an extra BIOS chip, and then you might have dual BIOS functionality on the card, which is really nice to have. That's really useful functionality to have on a GPU. I'm really sad that they decided to leave that out. Like, that really annoys me. So, yeah. Because ASUS, like, the thing is, ASUS have put out a unlocked BIOS for their GTX 1080 STRIX, which we will be doing in the future. I'm probably going to do that card tomorrow. They put out an unlocked BIOS for that card. And the thing about unlocked BIOS is, even if they're made by, like, ASUS or something, is, sure, the BIOS is safe, so there's, like, assuming the BIOS manages to flash properly, everything is fine, you know, there's no chance of breaking the card. The problem is, while you are flashing, if your power goes out, or your system crashes, or, like, you know, something goes wrong, you can end up in a really bad situation, and the worst of those is the BIOS flash fails to such an extent that Windows can no longer recognize the GPU. If Windows can no longer recognize the GPU, you basically, your only option to flash the BIOS is to find the BIOS chip, which I strongly suspect is this thing right here. And once you find the BIOS chip, is to basically solder wires onto it and flash it through a, using like a microcontroller, like say Arduino. Raspberry Pis can also flash BIOSes from what I've heard. Yeah, you know, you'd basically have to use something external to flash the BIOS, because Windows will no longer be able to talk to the card if something goes really, really wrong. So that's why, why it would be nice to have the BIOS switch, because if you had the BIOS switch, you could just switch over to the secondary BIOS. That would let you boot up, because you're not an idiot and haven't broken both of your BIOS chips, though I have heard of people who have done that. At which point it's just like, I don't know what they could do to protect you from yourself. Like, seriously. What? No switch, just like automatic BIOS recovery thing? Just write protection. BIOS write protection. That's the way to protect those kinds of people. Which AMD used to do that they would write protect the second BIOS chip. You couldn't write onto it. You could only write on one of the chips, which meant that the other one, you couldn't screw up the other one no matter how much you wanted to. Well, I guess you could stab it with a screwdriver or something, but you couldn't, like, flash it wrong. But yeah, so, like, having the BIOS switch would mean you could switch over to the uncorrupted BIOS, boot up on that, then switch over to the other BIOS and flash that. Because the BIOS for the GPU is only loaded up when the GPU initializes during the post process. After that, it's never used again. So you can actually switch the BIOS, like flick the BIOS switch while in the OS, and nothing really changes unless you tell the card to access the BIOS. And by access the BIOS, I mean like GPU-Z. When GPU-Z opens up, it reads the BIOS version, and it does that by reading from the BIOS chip. If you try to flash the BIOS and flick the switch in the middle of a BIOS flash, that's going to go really badly for you. But, you know, other than that, is like the BIOS chip is not accessed whatsoever. So you can actually recover really easily from like bad BIOS flashes if you have dual BIOS, which this card has the masking for it. They've just not put it on it, which I really don't understand why, because this is an expensive card. Kind of annoyed about that, but at the same time, at least it's nice that you might be able to hack it onto the card. Now then, let's take a look at the back of the PCB, because there is some stuff I want to cover on the back. And on the back, we find... Oh, what? Oh, GIMP. GIMP being GIMP. Okay. Oh, well, you'll just have to get used to that scribble being there. Wait. There we go. Fixed. So, on the back of the card, we have a few cool things. First of all, there's these empty pads for capacitors right here, which really convenient place to measure VCore. That's really, like, if you just want to figure out real VCore, you can just stab right there, which is much easier to do than trying to stab one of these, or even stab one of these. Like, these are relatively large, but it's still easier to just stab a flat pad of solder than trying to stab the side of a capacitor, especially considering all the little ones around it. Which, if you get the angle on your probe wrong, then you could end up shorting to ground, which is going to be very pleasant. So, easy place to measure, but it also means if you wanted to cap mod the card, like add extra capacitors to the card, you have a really, really convenient place to solder. And same goes if you want to add, if you wanted to, like, make your own voltage probe points, it's also convenient for that. However, that's, you know, that's sort of extras. Also, up here, we have something that looks suspiciously like ASUS's usual VCore and VMEM, and on the RX 480, it's VDDCI, which is the memory controller voltage, but here I'm going to be pretty sure it's going to be VPLL. So this right here is usually... basically, it's soldering points for all your volt mods, which is super convenient. Now, the problem is I don't actually have the card, and these are, as you can clearly see, they're labeled like XJ5, XJ3, XJ2. So they might not actually be the volt mod points, but I think they are. They're just not labeled so that people don't try to use them without basically being told by ASUS how to use them. But if they are those points, then it should make volt modding this card very, very easy, as you don't, like, soldering onto these holes, much, much simpler than trying to solder onto any SMD component somewhere on the card. That's just non-disputable. So that's really, like, assuming that's actually what it is, that's really nice and useful. And yeah, the other thing, which is just because I started, like, really working on a lot of power cards recently, one thing I noticed about this PCB is we have a really well-defined VCore plane here. Like, this is all VCore. Like, this rectangle right here, you can very clearly see that the PCB mask, well, that there's a copper plane right there, and that's all VCore. So that's really nice. And then you also have another copper plane, which, of course, like, spans the size of the card, but, you know, you get the idea. And that's all ground. And that means if you killed this card and couldn't get it RMA'd because you've done a bunch of mods on it, and, you know, good luck RMAing a card after you've hard modded it, what you could do is you could cut the card right along like here, and then you actually have a really convenient place to do all your like power board soldering when you're trying to connect this to another card, which admittedly that's not like an incredible feature to have, but I think it's kind of nice that it's an option just inherent to the way ASUS have laid out the VRM. Though you will have a problem in that you have to add the 5-volt rail to the card, so you'll have to add 5 volts and 3.3 volts and 12 volts, but that's standard for power boards. You always have to add those back. Well, actually 12 volts you have, but you'll have to add 3.3 and 5 volts. So yeah, that's kind of nice. And now let's go into the easy mod. Here's a shunt. Let's move to the front layer. There's a shunt. There's a shunt. And we all know what these do. These measure the current going into the card. These two right here, of course, measure the current through the 8 pins. The one on the back of this area measures the current coming out of this. And so basically, if you want to trick NVIDIA's idiotic, automatic overclocking algorithm into thinking that the card is pulling less power than it really is, you can put liquid metal thermal paste onto those shunts. That'll short them out, and that'll then lower their resistance, which basically means the card thinks it's pulling less power than it actually is. And you can, it'll basically allow you to boost higher. It also stops you from hitting power limits, depending on how far you can push the power limit slider in software. So it's a nice way to extend your power limits. And the thing is, so somebody asked in the comment section on a previous video, and I've addressed this a few times, but in a lot of NVIDIA breakdowns, but the reason why you short these out with liquid metal and don't short them out with like solder or something is because if you short these out with solder, the electrical resistance drops so low that the current reading through the shunts is so low that the NVIDIA driver notices that the power draw that the card is reporting is unrealistic, and the card goes into safety mode. And safety mode basically means the card is hard locked at 139 megahertz core clock, which is useless. So that's why you don't want to just straight up short them out. Now you could go and put another shunt across one of those. So if you wanted to like cut the power reading on this in half, then you would take another 5 milliohm shunt and put that on top of that, solder that in place, and you would have it would read half the current draw, and that's one way to do it. The thing is, if you're gonna do it with shunts, I recommend you buy multiple different size shunts and test out how low you can drop the resistance before the safety kicks on, because I'm not entirely sure where exactly it is that the safety kicks in. I think it's if you drop the power draw below 30% of what it should be. So you would want, like, if you added so that's a 5. So if you added 2 more 5 milliohm shunts on top of the one that's already there, then you would probably end up triggering the safety. And well, you'd actually have to do that for all the shunts on the card, but yeah. The problem is I haven't actually gotten a chance to do that mod because I don't have a 10 series card with a stupid safety thing, so yeah. Well, anyway, so that's the shunt mod. So you could solder it in place if you don't trust if you don't really want to have, liquid metal just sitting on top of a shunt somewhere. And speaking of the liquid metals, I've had one person report that they used Liquid Ultra, Cool Laboratory Liquid Ultra, and it ate the solder for the shunt. So that might be something you like. My solution to that is just go use Conductonaut instead. If you can't get, which is a Thermal Grizzly's alternative to Cool Laboratory Liquid Ultra, and if you can't get your hands on that, well, you might have to resolder the shunt back in place if it falls off, which is a really not a great option. So in that case, I'd say you probably don't want to do the mod at all. But yeah, it really depends. I don't think you'll need the mod unless ASUS puts out an unlocked BIOS. But if they put out an unlocked BIOS, then I expect the unlocked BIOS to have a very, very high power limit anyway, so you might not need the mod at all. So overall, I'd recommend you just wait if you can't get conduct to not. Or if you're going to be soldering, then, you know, you can solder. If you want to solder shunts in place, then there's no issue with that. Of course, that would void your warranty. The liquid metal, the other benefit of the liquid metal trick is that if you can literally just wipe it off with isopropanol or acetone, and I think ethanol would also work. I'm not sure. I know isopropanol and acetone work for sure. So you can wipe it off with those, and it looks like you never actually applied it. So it's a way to basically mod your power limit without losing your warranty on NVIDIA cards. So yeah, that pretty much covers everything I have to say about this card. And really the main reason I want this card is this thing, like, it might not be the overall super best. I'm pretty sure that we're going to see some cards with like 12-phase VRMs and 16-phase VRMs. EVGA is certain to put out a 14-phase, and but the reason why I like this one a lot is basically there's a lot of stuff to tinker with on it, and I'm not talking about the shunts because you can do that on all the NVIDIA cards. I meant more like the location of the capacitors, the volt mod points, well, what I assume are volt mod points, the BIOS switch thing, the fact that if I kill the card, I can actually save the VRM relatively, like, you know, it's not as painful to try rescue the VRM off of this thing as, say, off of some of the other cards, just in terms of how it's laid out. As far as actually hot wiring it, well, luckily ASUS hasn't rebranded the voltage controller. It's a UP9511, so you can actually get a data sheet for that, so there's no problem with that, which would in the past, on past ASUS cards, you'd have a Digi+ voltage controller, and then if you tried to volt mod it, then, well, if you tried to saw off the VRM, or even just volt mod it, you'd be in, like, have a really hard time because, well, there's no data sheets for the Digi+ branded voltage controllers. So yeah, and I think this video has run on enough at this point, so thank you for watching. Like, share, subscribe, leave a comment down below about, you know, anything that wasn't clear in this video that you would maybe stuff. You know what to leave in a comment, damn it. And yeah, that's it. Thank you for watching, and see you next time.